In this slide, we will show an example for floating point numbers, and we want to create a hypothetical floating point number set for a machine which stores the information using 7-bit words. So this word has 7 bits, as you can see, as an example, and we want to use the first bit as the sign of the number. So here, sign of the number, and the next 3 for the sign and magnitude of exponent. So the first one for the next 3 will be sign of exponent, and the next 2 will be the magnitude of the exponent, and the last 3 for the magnitude of the mantissa. And you can see the rest 3 is the mantissa. So for this example, on the right hand side, the sign is 0, meaning it is positive. The sign of exponent is minus, and magnitude is, we can define the magnitude as well. So magnitude starts with, for this exponent, 2 to the power 0 and 2 to the power 1. So that's why we can just 1 times, so this is 1 times 2 to the power 1 plus again 1 times 2 to the power 0. If we sum this, E is actually from here 3. Also, magnitude of mantissa here on the right side, and these are going from, the biggest one is -1, as you can see here, then -2, -3. For mantissa, always it is because fractions, like after the point. That's why it starts from -1 always. Keep this in mind. And if we write these, there is only this one actually, because the rest is 0. 1 times 2 minus 1, and this becomes 0.5, and that means m is 0.5 for this example. So if we write them all for this example, m times b to the power e equals 0.5 times 10. Of course, e is minus because this is minus, and this is plus, this is because it's plus or positive, -3. This is our number. Or if we write this, expand this, it's minus 0.0625. Sorry, not minus, positive. Because number is positive, exponential is minus. Right, again, 0.0625. So actually this value is the smallest positive number that can be represented by this 7-bit representation, because m is 0.5. If you remember, our rule was the m should be bounded by 1 divided by b, which is 2 here, smaller than m, and equal m, this, and m is smaller than 1. So this is actually 0.5 m1, and m is 0.5 here already. So this is the smallest. You can see we cannot go below this. Actually, in numbers here, for example, if we write 0 here and 1 here, we can go below this value, and this can be smaller, but it cannot be represented by this 7-bit words, because the smallest should be 0.5. We can show this on the right and left hand side. Here, let's say, so let's represent this floating number as the base 2 system. This is 1002, or this means 0.0625 in 10. This is the smallest, is the smallest positive, which can be represented by 7-bit words. But there are smaller, and the reason is this, but there are smaller numbers. There are smaller numbers, but they cannot be represented. Let's show that. For example, or let's say, but m has to be between this values. So let's show the numbers. For example, if we write this as in a similar way, with 0 sign and 1 for exponent sign and 1 1 for exponent, and 0 0 0 as our number. So here is the number, and the result of this is 0. But this is, this is much more smaller than 0.5, and this is m equals 0 anyway. But m equals 0 means this is smaller than 0.5, this smallest result, and this cannot happen. Similarly, 0 1 1 1 0 0 1, for example, the same. And in here it is just this is, we can say here as well, 2 minus 3, here 2 minus 3, and this is m equals 1. Sorry, m is minus 3, yes. M is not equal 1, but 1 times 2 minus 3. Then from the exponent this times from the m this, and from the exponent minus 3 as well, it is 0.015625. This is again smaller than 0.5, which is the lower limit, so this can't happen as well. Similarly, 0 1 1 1 0 1 0 and 0 1 1 1 0 1 1, these are also, let me write the results quickly. You can calculate them if you want as a practice. 0.046785, and these are all smaller than 0.5. That's why these are not useful. We cannot use them. And after this, the next highest is this value, and it is exactly 0.5. That's why we can start with this. This is the smallest positive for this reason. So in here we can also start from m.5, increase the numbers. Let's try to do that here. The next higher numbers, and for that we will just change this as 101, for example. The first one can be that, and the beginning is the same, 101. And if you calculate this is equivalent to 0.078125 in 10. Then we can increase one more. These are the same, but the mantissa can be 110, and here 0.093750 in tens. Again we increase once more. These are the same, but this is 111. We keep increasing. 0.609375. This is again 10. And the interval here, so we can show this way, from this to here, interval, the increase of interval, or interval increase, (0.01561). They increase with equivalent intervals, let's say. There are further numbers, but the interval increase is changing. Let me show that to you. If we try to further increase this at the bottom, then we will need to change the e value. Actually, here e value is -3, we can change it to -2. And how can we do this? Let me show. The beginning is 0, and this will change to 1, 1, 0. And here we will start with the smallest number, and the smallest we know that was this one. So we will write the same, 1, 0, 0. And if you calculate this, from here actually it comes, you can see minus and only 1, which means only 2. So this brings us the value of 0.125, and we will keep increasing using these values, and we will keep the exponential the same, 0, 1, 1, 0, just 101, then 0, 1, 1, 0, 1, 1, 10, sorry, 1, 1, 0, 0, 1, 1, 0, and 1, 1, 1. And if you calculate these, you can simply calculate using this information here by multiplying and summing for exponent and mantissa, and the results are 1, it has to be 1, 0.15625, 0.1787500, and 0.21875. And you can see the interval here. So interval increased from here to here differently, but in these four the interval is the same, and interval of only 0.03125. So here it was 15, here 31. So after this it will increase further. Let me write it down to this empty space. Let's increase further, and for that we will actually reduce exponential. So here the exponential was 111, here 110. Now we will make 100 maybe. Or actually I skipped that and I wrote 011. So let me write that down. So I skipped some numbers and moved to the positive exponents, and for those, let me write with blue. 0, now 011 here, this makes the exponent positive, and 11 makes the exponent as 2 to the power 3 and in a positive way. So it is similar as this, but this is 0 only. So we will keep using the same values for the mantissa. 100, 0011, 101, 0011, 110, and 0011, 111. And if you calculate these, I will keep short calculating. I will not calculate them, but you can try simply using these values like I did here. And the results are actually here 4. Let me calculate the first one. So this first one is simply this exponent and mantissa. Mantissa is basically only 1 for the to the -1, which gives us 1 times 2 minus 1 times base system is 2 and exponent is 2 again, but this time positive. Here it was -3 with these. Here it is the same here, but positive, so it's 3 here. That means 0.5 times 8 equals 4. So same here, 5, 6, and finally 7. And 7 is the number that we can as the maximum. So this is the maximum number that we can represent with this 7-bit notation. So you can define all the numbers as shown here for floating point representation. for example, a 7-bit, but for 16-bit. And also we should mention that the increase in here is intervals are 1, intervals of 1. We can see that intervals were smaller, then getting larger and got larger. We can only demonstrate these values with this 7-bit computer demonstration. So this is very limited actually. That's why we currently use larger bits for the computers, and especially 32 and 64, especially 64-bit machines are now popular. That's why we use them. And these can represent all the numbers that we want actually.